Welcome back to the deep dive. We're here to, cut through the noise and find those aha moments. Today, we're diving into something huge, something we use constantly but maybe don't think about too much, the internet. I mean, really think about it. Messaging, streaming movies, running global businesses, even major research projects, it's just there, always on. But have you ever actually stopped and wondered how it all works? Like, what's really going on in that invisible world of cables and servers and signals keeping us connected 24/7?
It really is quite something. It feels so seamless, almost like magic, right? You click and stuff appears. But underneath, it's this incredibly complex web of technology, rules, physical stuff connecting everything. Our sources show it's way more intricate and frankly more robust than most people probably imagine. It's fascinating when you start peeling back the layers.
Exactly. And that's our mission for this deep dive. We want to get past the basics, unpack how the internet really functions using what our sources tell us, give you that shortcut to understanding the engineering marvel behind every single click and swipe you make. Okay, let's get into it. Let's pull back that digital curtain. So when we say the internet, I think a lot of us, maybe subconsciously, picture this one giant brain somewhere, like a single massive computer running the whole show. We kind of know that's not right, but the sheer scale makes it feel like that sometimes.
Yeah, that's a really common misconception.
Yeah.
But it's definitely not one big computer. Not at all.
Well.
Think of it more like a gigantic network made up of millions and millions of smaller networks. And these networks connect all sorts of devices, your phone, your laptop, huge servers and data centers, even satellites way up there. The name itself, internet, actually means interconnected networks. That's literally what it is. And this whole decentralized idea wasn't an accident. It was designed that way from early on for resilience. So if one part fails, the rest keeps going.
Oh, okay. So less like one central brain and more like a massive ongoing global conversation happening everywhere at once between all these different devices and networks, right? And that makes sense. So if it's this huge, sprawling conversation, here's the really interesting bit. How does the information, a message or a video, actually travel
Wow.
across continents, sometimes in like seconds? How does that happen?
Right, the speed is amazing. It comes down to this core idea called packet switching.
Mhm.
When you send something in email, let's say it doesn't go as one big block of data, your device actually chops it up into these tiny little pieces called packets. Think of each packet like a tiny envelope. It's got a little bit of the data, the destination address, and instructions on how to put it back together with all the other packets.
Okay, little digital envelope.
Exactly.
Yeah.
And our sources really stress this. These packets don't all have to follow the same route. That's key. They can travel across the world using totally different paths. Some might go through undersea cables, some bounce off satellites, others via cell towers, whatever's fastest or least congested at that moment. Then, when they all arrive at the destination, your device cleverly puts them back together in the right order. You get your email or your video starts playing.
That's wild. So it's like tearing a book into individual pages, mailing each page separately using different couriers, maybe some by bike, some by plane, and then the recipient somehow gets all the pages and instantly reassembles the book perfectly.
That's a pretty good analogy, yeah?
And all of that happens, that whole complicated delivery system, in just milliseconds after you hit send.
Pretty much, yeah. Milliseconds. The efficiency is incredible, but it's also about resilience. If one path is blocked, the packets can just find another way.
But what if, using your analogy, what if a few of those pages, those packets, get lost in the mail or arrive super late? Does the whole thing break down?
Good question. The system's actually designed for that. It's pretty robust. See, packets usually have sequence numbers and ways to check for errors. If the receiving device notices a packet is missing or maybe corrupted, it can just ask the sender to resend that specific packet.
Okay.
So losing one packet usually isn't a disaster for, say, loading a web page. But if lots get lost or delayed, that delay is called latency, that's when you might see buffering on a video or lag in a game. It's a trade-off.
Yeah.
Speed versus making sure everything gets there correctly.
Fascinating. Okay, so these packets are whizzing around, finding their destinations, but where is the destination for all the stuff we look at online? Websites, videos, articles. Where is it all stored? This brings us to the servers, right? The internet's libraries, you call them.
Exactly. Servers, you can think of them as digital libraries, yeah.
Uh,
But they're really just very powerful, specialized computers.
yeah.
Their main job is to store information, websites, videos, databases, whatever, and then serve it up when someone requests it.
So like a librarian fetching a book.
Precisely. But these aren't usually single machines sitting in an office. We're talking about huge buildings, data centers, filled with racks and racks of these servers. Our sources describe these places climate-controlled, massive power backups, super high security, often strategically located around the globe. So every time you open a website, your device sends a request out across the network to one of these servers, this digital librarian,
Yeah.
and the server finds the data you asked for and sends it back to you, broken down into those packets we talked about.
The scale of that is just hard to grasp. Billions of people, billions of devices, all sending requests constantly to countless servers all over the planet. It's this massive, constant exchange of information, incredible coordination needed. But okay, here's another puzzle piece. With all these millions of servers out there, how does my computer know which specific server to ask for, say, thedeepdive.com? How does it find the right address in this enormous global city?
Right, navigation is key. This is where we get into IP addresses and something called the DNS. Every single device connected to the internet, your phone, a server, even the routers in between, gets a unique number. That's its IP address, like a street address online.
A string of numbers, right?
Yeah, traditionally it's been numbers like 192.168.1.1, that kind of thing. That's IPv4. But as our sources point out, we've basically run out of those IPv4 addresses because there's just so many devices now.
Really run out.
Pretty much, which is why we're moving, or have largely moved, to IPv6. These addresses are much, much longer, giving us a practically unlimited supply. Think
Yeah.
trillions upon trillions.
Okay, got it. Lots of numbers.
But the problem is nobody wants to remember long strings of numbers, right?
Mm-hmm.
Imagine typing 172.216.160.142 just to get to Google.
Okay.
Exactly. So we use easy-to-remember names instead, like google.com or thedeepdive.com. These are called domain names. Now, the system that connects the easy domain name to the difficult IP address number is the DNS, the domain name system. Think of the DNS as the Internet's giant distributed phone book. It's not just one book, it's spread out all over the place.
A phone book for websites.
Kinda, yeah. When you type a domain name, your computer asks the DNS system, hey, what's the IP address for this name? And the DNS system looks it up and sends back the correct numerical IP address. Then your computer knows exactly which server to contact.
And this phone book lookup, it happens like instantly every time I type a web address.
Almost instantly, yeah. Usually milliseconds. It's a series of quick lookups happening behind the scenes. Your computer might check its own memory first, then ask a local DNS server, maybe then a bigger one. It's a whole hierarchy.
Wow, that's amazing. It's this fundamental piece that just works, and we never even see it. But you said it's distributed. Does that make it vulnerable? Like, what if someone messes with the phone book?
That is a really important point. Being distributed makes it resilient. No single point of failure. But parts of the DNS can be attacked. We've seen massive cyber attacks like DDoS attacks, target DNS servers. If they succeed, even if the websites themselves are fine, nobody can find their addresses, so huge chunks of the internet become unreachable.
Oof.
Yeah. So there's a constant effort to make DNS more secure, using things like DNS-SEC, which adds digital signatures to prevent tampering. It's like an ongoing security race. Without a working DNS, the internet we use just wouldn't function.
Okay, that really highlights how interconnected everything is. Now, thinking about my connection, most of us use Wi-Fi at home or mobile data on our phones, right? It feels very wireless, like the data is just floating in the air. But that's just the last little bit, isn't it? What's doing the real heavy lifting when data has to cross oceans or continents? What's the backbone?
That's a great distinction to make. Wi-Fi, 4G, 5G. That's what we call the last mile, getting this signal to your device. But it's just the entry ramp onto a much bigger highway system. And that highway system is overwhelmingly physical. The real heroes, the ones who do almost all the long-distance work, are hidden from view. They're undersea fiber optic cables.
Undersea cables, really?
Absolutely.
Yeah.
Our sources consistently show this amazing statistic. Something like over 95% of all international internet data travels through these cables laid on the ocean floor.
95%. Wow.
Yeah, we're talking about bundles of hair-thin glass fibers carrying data as pulses of light at incredible speeds, stretching for thousands and thousands of miles between continents. They're buried under the seabed, crossing the Atlantic, the Pacific, everywhere. That's the true backbone.
So even though my connection feels wireless right here, the journey across the globe is mostly wired, hooked up by these massive physical cables lying on the bottom of the ocean.
That's exactly right.
That's just staggering, the engineering to lay and maintain those. And I guess that means these cables are pretty important, geopolitically speaking. Who owns them? Where did they land?
Oh, absolutely. It's hugely strategic. Countries and big tech companies invest billions in laying new cables. Where they land, who controls them. That's a big deal for national security and economic power. And they can be damaged to earthquakes, ship anchors, even sharks supposedly bite them sometimes, so that might be a bit of a myth.
Sharks, seriously.
Well, maybe anchors are more common. But yeah, disruptions happen. That's why there's so much redundancy, multiple cables, different routes. So if one breaks, traffic can hopefully be rerouted quickly. But it shows, the internet is very much grounded in the physical world.
Okay, so we have data in packets, finding servers via DNS, traveling mainly through physical cables. But this is often our personal information zipping around, banking details, private messages, sensitive work stuff. How is all that kept safe while it travels across these, well, often public networks? What stops someone from just grabbing those packets out of the ocean cable, metaphorically speaking?
Security is absolutely crucial. You've nailed a key point. The main tool we use is encryption. Most websites you visit today, especially anywhere you log in or buy something, use HTTPS. Yeah, because S stands for secure. You see the little padlock in your browser.
Yeah, I see that.
So what HTTPS does is create a secure, encrypted tunnel between your browser and the server. Before any actual data is set, they do this kind of secret digital handshake using complex math. This process ensures a few things. One, confidentiality. The data is scrambled, so even if someone intercepted it, it would look like random nonsense without the secret key. Two, integrity. It guarantees the data hasn't been messed with along the way. And three, authentication. It helps prove you're really talking to the genuine website, not an imposter.
So it's like a secret code and a verification check all rolled into one, happening automatically.
Pretty much, yeah. It's working constantly behind the scenes to protect your information as it travels.
That's actually very reassuring, knowing that invisible lock is working whenever I see that padlock. It builds digital trust, doesn't it? You need that for online shopping, banking, well, everything really.
Absolutely. Without that trust, which encryption provides, the digital economy just couldn't function like it does. And it's not static either. Security is always evolving. As computers get more powerful, old encryption methods can become weak. So researchers are constantly developing stronger algorithms, new protocols. It's an ongoing battle to stay ahead of potential threats.
A constant digital arms race, basically.
You could say that, yeah. Plus, you have other layers, too, like firewall, spotting intrusions, and just users being careful about things like phishing scams. It all works together.
Okay, so let's bring this all together. Next time you send a quick message or stream a movie or just search for something online, pause for a second. Remember what's happening behind the screen. Your request, your data, isn't just floating wirelessly out there. It gets broken into tiny packets, gets an address from the DNS phone book, finds its way to a server, probably in a massive data center somewhere, travels maybe thousands of miles, likely through cables deep under the ocean, gets reassembled, and comes back to you, all secured by encryption.
And it all happens unbelievably in fractions of a second, just milliseconds. The internet. It might seem invisible, intangible even, but as our sources make clear, it's one of the most complex, sophisticated, and frankly impactful things humanity has ever built. It's a testament to decades of innovation, engineers solving problem after problem, connecting us all in ways we couldn't have imagined just a short while ago.
It truly is. More than just amazing engineering, it's changed everything, how we think about distance, how we form communities, how business works, the very fabric of connection. So here's something to think about. If this is the interconnected network we have now, built on cables and servers and packets, what kind of new networks, maybe even more integrated, more complex, will we build next? And how will they change what it means to be connected?